Okay, this is going to be part 2 of the run-through for this Edexcel Linear AS Core Physics 2 paper from 2019. It's the one I'm working through with my students to prepare them for the end-of-year exams and the AS papers, actual papers, if they're taking it. Okay, so this is good practice for what's to come ahead in year 13. And once again, if you saw the first part and it's in the same playlist, if you haven't watched it yet, you may want to go and watch that first. I go through the first 12 questions, which includes the 8 multiple choice and the 4 structured questions which precede the question 13 I'm going to start with now. If you watch the videos, you find them useful, please help to spread the word for this channel and share it with any friends who are doing physics either at AS level, A level, linear or modular, or if they're doing GCSE, there's also some IGCSE papers, the recent ones 2023 and 2024, if it helps them with preparing for their exam. So be grateful if you do that. Thanks very much. Okay, we're over 1,000, we're nearly 1,100 subscribers, and that's pretty good considering I only started the channel 14 months ago now. January of 2024, whatever that is. Maybe it's 15 months. Okay, here we go, straight into the first question in the part 2 of this run through, question 13. Okay, so the diffraction of light provides evidence for the wave theory of light. So this is about wave-particle duality, but it's talking about the wave theory. The diagram represents wavefronts of light, incidents at a single slit. Okay, so if a ray is a single forward arrow, the direction of a narrow beam of light, wavefronts are at right angles to the ray. Okay, and they're going to ask you what is meant by wavefront first. The points labeled A, B, and C are points on the wavefront that has just started to pass through the gap. So here's the gap from A to C, and the wavefronts, you can see the distance between them represents the wavelength, and they first of all want you to describe what is meant by a wavefront. Okay, so the way I've answered it, it's a line drawn to join all the points along a wave which are in phase with each other. Yeah, example, the peak of a wave. All the peak of the wave are points in a wave which are traveling in unison together towards the direction that the energy is flowing. Okay, so that's a good way of remembering how to explain it. And when you do these questions, you should go back and improve your notes to bring clarity to these ideas. So if you haven't got clear notes on the wavefront, you need to make sure you've added them in to your final revision notes that you want to look at before you go into your real exam. The next part says, add to the diagram above to show how Huygens construction can be used to determine the shape of the wavefront, the next wavefront, after the wave has passed through the gap. Okay, so here's the gap, and they want you to show what happens to the wavefront. It was straight when it was before it went through the gap. It's straight as it goes in the gap, and then what happens? Well, what you got to do to understand Huygens construction, yeah, is to understand that every point along a wavefront can be, so say we take this wavefront, the first one here, every point along this wavefront can be considered to be a point source of secondary wavelets. Okay, and a wavelength is a little wave, so if you think of it as a point source, this, you can draw semicircular wavelets, yeah, at A, B, and C in between the gap. So if this was A, B, C, D, E, F, each one of these would have a semicircular wavefront, yeah? And you should draw them equally. And then a tangent drawn would be the new wavefront that they were going towards. You see, a straight wavefront will produce a straight wavefront using Huygens construction, yeah, as every point on the wave being a point source of a circular wave, because remember, point sources produce circular waves. So they want you to draw semicircular wavelets at A, so centered at A, I've drawn one there, centered at B, and centered at C. Yeah? Obviously you can't go beyond A or C because there is the obstacle which shows that there are no other point sources of the wave beyond A above and beyond C below the points that I have drawn. If you draw all three, A, B, and C, you get 2 marks. Yeah? And you should really draw the radii of the wavelets to be equal to the distance between the wavefronts before the slit. So you see the distance is from here to here, so that should be roughly the size of your wavelets. Okay? And then what you do for the last bit, I'm going to highlight it in yellow because I've written in green, the final point. New wavefronts, yeah, drawn with the shape as shown, yeah, so you then put a tangent to all of these wavelets, as I have drawn in green, yeah. You then join all the tangents with a straight line, so you could actually put a ruler there and put it there. So you draw all the tangents and then you curve them at the ends where there are no more wavelets. And that's how you draw the new wavelet. So you see it's curved on the edges and straight in the middle. And that's how you use Huygens construction for points A, B, and C. Now, the more points you have, the better it is, in fact, but it's a really good question to learn from, to use Huygens construction in this question, because it's made it deliberately simple and made it only 3 marks. So first thing, you need to know what a wavefront is. Secondly, you need to know how to do Huygens construction, and it's usually used to explain diffraction. The next part of the question says, a student carried out an investigation to determine the wavelength of light emitted from a laser pen. He shone the light from the laser pen so that it was incident perpendicularly on a diffraction grating. So this is another core practical. So let's put that in. So you see the core practicals don't just come in the practical exam, they come in the theory. The diffraction grating had 200 lines per millimeter. So you've got to work out what D would be in millimeters. Would be 1 over 200. Yeah? So D is the distance between 2 adjacent spacings or slits in the diffraction grating. He observed the diffraction pattern on a screen 3.00 meters away, yeah, from the grating. So the screen distance was 3.00 meters, which is common. The pattern consisted of a series of bright dots. Okay, so this is D in the equation. Yeah, and here and that's big D is to the screen, little d is the spacings or the distance between adjacent slits in the diffraction grating. So the first question says, give a reason why a laser is a suitable source of light to produce a diffraction pattern. So remember, for diffraction to work, or interference to work, you need ideally monochromatic light, single wavelength, and of coherent light. That means that they have a constant phase relationship. So really you want it to be the same source that can go through the slits, okay? And it's the same when we did Young's experiment, okay? So if you see the central fringe is n equals 0, and then you've got the bright fringes to each side, and I've drawn them to the right, okay? And they've given us later on in the next question that the distance between n equals 0 and n equals 3 from here to the center here is 1.02 meters. So that must be in the next question. There you go. It says the distance, the student measured a distance 1.02 centimeters, 1.02 meters, 102 centimeters between the central maximum, which is n equals 0, and the center of the third order maximum, which is where n equals 3 in the equation, which is n lambda equals d sine theta. Okay, that's n in this equation. Little d we've already talked about in the introduction, yeah, and lambda is the wavelength, and sine theta is the angle it makes from the center. The table shows the range of wavelengths for each color of the visible spectrum, yeah. So you got all the colors from violet down to red, and the range of their wavelengths of what we define to be violet and each of the colors in the rainbow. Okay, so we've been given information, so I like to write everything I'm given. We know D in meters would be 5 times 10 to the minus 6 meters, yeah, because it was 5 times 10 to the minus 3 millimeters, so it's going to be in meters 1,000 times smaller. N we want is 3, yeah, so we need to use n as 3. Theta, see below, is going to be 18.8 degrees for n equals 3, I think. Oh no, theta, yes. We want to find tan theta. So tan, yeah, for n equals 3, the angle I worked out is 1.02 is the opposite, so on the screen, and it's 3 meters away. So you can work out the angle is 18.8 degrees, which gives us some arc, and that's what I've put down there. So we know theta. So once you use tan to work out the theta, then you put the theta into this equation and you use it as sine. And in this equation we know n equals 3, and the only unknown then we have is lambda. So you can put the 3 on the other side, put 3 down there, put all the numbers in, and you will get a wavelength of 5.37 times 10 to the minus 7, which is in the green range. So let's make that green, the green range. You can see it's in nanometers, that's 10 to the minus 9, and we've got 537 nanometers. There's an alternative way of writing 5.37 times 10 to the minus 7, 5.37. So it's in the green range, so it's green light, and there you can see where I've given the ticks is where you get the marks. Should be hopefully 5 ticks there. 1, 2, 3, 4, 5 is what I see, and then you can go and check that on the mark scheme at the end. That gives us 10 more marks. Question 13 done. Okay, question 14. I'm going to have to go through the whole paper in one sitting because it's getting a little bit late. and this work tomorrow morning. So the next question, it says an optical microscope uses a beam of visible light. An electron microscope, on the other hand, uses a beam of electrons. Now this is again the wave-particle duality, that you can get electrons to have wave-like properties. A biologist looked at an animal cell using both microscopes. Okay, here's the image using an optical microscope, and here's one using the electron microscope. Okay, the two images are shown. Both have the same magnification. Okay, that's interesting. So it says an electron in the beam of electron microscope has a velocity which is 2% the speed of light. Okay, they've given you that. So we know velocity, you can work out 0.02 c will give you a velocity of 6 times 10 to the 8 meters per second. So maybe that gives you a mark, I haven't checked. And then we know they want us to calculate the de Broglie wavelength of the electron. De Broglie was a French scientist, I believe that's how you pronounce his name. To work out the de Broglie wavelength, we need to use the equation, lambda equals Planck's constant divided by momentum. Well, we just know the velocity, and the mass is given to you in your data sheet. So we know that the data sheet provides the mass and also provides Planck's constant. So once we know basically everything to be able to work out the answer, you put your numbers in from your data sheet, plus the velocity that we just worked out. So the bottom is, the bottom of this equation is mass times velocity, and the top is Planck's constant, so that gives you a value of 1.2 times 10 to the minus 10 meters for the wavelength of the electron microscope electrons. Now, as you can tell, 10 to the minus 10 compared to visible light, which is 10 to the minus 7 meters, is 1,000 times smaller than the wavelength of using the optical microscope. Okay, so I should really put that in this space. All right, the image, it says, of the animal cell produced by the electron microscope is less blurred than the image produced by the optical microscope. Explain why. So these are the points I've put. The wavelength is smaller and therefore has a greater resolution. But I think the mark scheme have put it differently to this. So I don't know if I'd get the 2 marks looking at the mark scheme, which you can do later on. They mention that it diffracts less. That is smaller. So diffracts less when it's going through the cell tissue, I think they mean. Okay, so they mentioned that it will diffract less. We'll have a look, and then we'll have see the best way of answering these 2 marks. So I might only get 1 mark for my answer, but I do know that a smaller wavelength means higher resolution, and that's the normal way that we get these marks. Okay. So the biologist measured the diameter of the cell from one of the images. Okay. He recorded 4 measurements, and the image had a magnification of 800 times. All right, well, you notice that he's got 4 values, 2.4, 2.5, 2.2, but in the middle there's a 1.1, very anomalous, so you should remove it because it's really way out, it's not even close. And then you should work out the mean of the other 3 and really you should give it to 2 significant figures to be consistent with that. The actual average is 2.37 if you want to be more accurate in your initial calculation, but then you should round it up if they're asking you to make that your final answer. So the magnification obviously is something that we've been given 800 times. So we know the image diameter must be 800 times the actual diameter. So if we want to work out the actual diameter D, we got to divide the value, the mean diameter of the image, yeah, because remember we're talking about the image. You take the mean value and divide it by 800 and you'll get the real diameter. So I just decided to use my accurate 3 significant figure value, and it comes to 2.96 times 10 to the minus 3 centimeters. I left it in centimeters. If you want to put it in meters, you just have to change it, yeah, because if you're just comparing centimeters to centimeters, you can use centimeters because obviously it will just be 800 times smaller. So the 3 significant figures, that's what you get, either centimeters or meters, and then you should probably round it up to 2 significant figures, which will give you 3.0. Okay, so that's another 7 marks, and that ends the total for the structured questions for section A, and that's 60 marks out of 80 of the paper completed. Section B, then, in the linear, can be on any topic in year 12, so it doesn't have to be for core physics 2 on waves and materials only. It can be electricity and topics that you studied in mechanics as well. So we'll have a look at those in a minute, but let's just go and have a look at the mark scheme for these questions. We want question 13. So there's question 13. So there you can stop the video and have a look at what they say are the marking points. Question 13b on the next page. So it's about the laser light being green. Question 14, use of the momentum for de Broglie and the wavelength of the electron. Yeah, so they said that the wavelength of the electron in the answer, the wavelength of the electron is less than the wavelength of light, 1,000 times less. So there'll be less diffraction with the electron beam, and they haven't given enough detail as far as I'm concerned. Yeah, they haven't mentioned resolution. So a smaller wavelength creates a better resolution. Anyway, then they're then talking about the wavelength of light is greater than the wavelength of the electrons as the or part of this answer. So more diffraction. So they want you to use diffraction in this answer, whereas I think we should use resolution. And the smaller the wavelength, the better the resolution. Yeah, which is what they were asking about. And then the image, talking about that was quite simple, no controversy there. And now we're in the final 2 questions, 15 and 16. So let's go straight back into questions 15 and 16 before the mark scheme. There we have it. So question 15 of section B, it says read the passage. So it has a passage which threw some of my students the first time they saw it. So, and it's even gives you references from Physics Review in 2015. Yeah, it says that this is some kind of test. The Sharpie test is used by scientists to measure the fracture toughness of a material. Yes? So basically when it fractures under the action of this hammer that falls on a sample that's placed here, so you're using gravitational potential energy, yeah, and this is the height, yeah, which is mg delta h. It loses height, hits the sample, and they test it that way. A simple pendulum method with a hammer at the end is held high and released so that it swings down and strikes the sample which is placed in the center of the swing. The height from which the hammer is released is increased until the sample fractures. Okay, so you can see there's some kind of measuring tool with the angle at which you can tilt it. Okay, some energy is absorbed by the sample in the impact, but so that's the delta E, the energy absorbed I've put. But the hammer continues to move until it comes to rest at the top of the swing on the other side. Okay, so you can see the height difference here is obviously less than the height that it starts off with, the initial gravitational potential energy. So it maintains some gravitational potential energy afterwards related to the height above the sample that it moves through. Due to the law of conservation of energy, the hammer will not swing up as high as its starting position. The difference in height between the start and the end is proportional to the energy absorbed, delta E, if you like, in the impact. So, the impact, which is the fracture toughness, that's what they've put. So the difference in height will be delta H, I've put here, which is H2 minus H1. Yeah, I should have put H1 minus H2, I think. I've got it the wrong way around if you see my diagram. So that should be H1 minus H2. All right, the difference in height between the start and the end is proportional to the energy absorbed in impact. And that's called the fracture toughness. Okay, so there you go. That's the delta E I was referring to. Justify this statement. Well, it makes sense. The gravitational potential energy at the start is the energy absorbed plus, goes to the energy absorbed plus the gravitational potential energy left as it swings through onto the other side. So the fracture toughness, if you like, is delta E that they're calling, yeah, the energy absorbed in the impact is delta E, is equal to mgh2 minus mgh1, which will be the difference in the height from before till after. So the energy absorbed is proportional to the height difference. Yeah? That should say delta H here. Okay? So I think this will justify the statement. These points will justify the statement. And you'll get your 2 marks if you can put this in a clear manner on the paper. Part B then says the hammer is released from a height of 13.0 centimeters above the lowest point of the swing. That's H1, and that should be in meters. Calculate the momentum of the hammer when it reaches the sample. The mass of the hammer is 31 kilograms. So we know the mass, and you got to calculate the momentum. So we know that it basically changes from potential energy to kinetic energy before it hits the sample. So you can just cancel the m's out, and you can then put V equals the square root of 2gh, which is a common equation for A level. Put the numbers in. Make sure you put the h in meters in this equation, which I have, and you'll get a velocity of 1.6 meters per second to two significant figures. You put the value into momentum, and the mass also goes in there. The answer then gives you to three significant figures 49.6 kilogram meters per second, and you could round that up to two significant figures, which would be 50 kilograms meters per second. So that's the first of the section B questions, I think. Oh no, there's a bit more. And this time they're giving you some data. The sketch graph shows how the fracture toughness of a sample of steel varies with temperature. Okay, and let's have a look at the temperature. Temperature goes from minus 40 all the way up to plus 50. So that's the temperature variation. And you can see the fracture toughness is greater, so it's tougher at a high temperature, and at low temperature it has a lower level of toughness. Okay, so a material with a low fracture toughness can absorb less energy, before fracturing than a material with high fracture toughness. Okay, so the ship Titanic sank in 1912 following a collision with an iceberg in the icy waters of the Atlantic. Icy, what they're doing, they're talking about the low temperature end, and remember we're talking about steel in this question, and the Titanic was largely made of steel. The steel hull of the ship was fractured by the impact. Deduce why the steel was likely to have been fractured by the impact. Okay, well, first thing is you want to mention the low temperature produces lower fracture toughness, yes, as you can see from this side of the graph. Okay, and less energy can be absorbed before fracturing at low temperatures. So a collision at such temperatures, cold waters of the Atlantic, would increase the chance of fracturing. So would I get 3 marks? You'd have to go and see on the mark scheme for 8 marks. So section B, the first question, question 15 is done, and 8 marks later we're into the final question of this exam paper run through. Okay. All right, so it says question 16, the final question. A solar panel uses electromagnetic radiation. So E equals HF would be what you need to use from the sun to generate electricity. So photons are coming in. In one installation, a sensor in the control panel measures the intensity of radiation arriving from different directions. A motor rotates the solar panel so that it always faces the brightest part of the sky to maximize efficiency. Okay. It then goes on to say the intensity of the radiation incident at the surface of the Earth is about 1100 watts per square meter. The intensity equation from waves is the power in watts divided by the area in meters squared. Okay, so that's the 1100. So the solar panel, it says, has an area of 2.4 meters squared. So that's the area that we need. Radiation is instant on the solar panel at an angle of 50 degrees as shown. So here's the 50 degrees. Okay, now we would ideally like it to be at right angles. Okay, and then the efficiency of the solar panel is 20%. So efficiency means this, useful output, divided by the power input. So it could be in watts or in joules. I was going to do energy, but in fact we need to use power, because power is in the equation here. All right, so calculate, it says, calculate the electrical power generated by the solar panel. Okay, so that's our useful output. But the power input is going to be from this equation. The power input is from that equation, and is equal to the intensity times the area, but you've got to take into account that it's at 50 degrees, and therefore to get the perpendicular intensity, so if it was directly overhead, there's a sine 50 involved, because you want it to be perpendicular, so you're going away from the angle. And if you're going away from the angle, so you want the light to come in straight down, so it would be cos 40, so you want it to come in this way. Yeah? So I don't know if I've drawn that exactly perpendicular, but you get the point. If the light was coming in this way, and it would be perpendicular to the surface, you would get the full effect. Well, because at angle 50, you've got to bring in the sine of 50, okay? Or the cos of 40. And once you do that, it's like resolving the direction of the light coming in. You put the value of 1100, which we're given in the question, multiply by the area which we're given in the question, and you've worked out sine 50, yeah? And that's the thinking you've got to do, and you'll get 2020-ish watts output, okay? So I've given you a 5 significant figure value, in fact, and I'm doing that deliberately to show you when you give your final answer, you then change it to the right number of significant figures. And a power output, if that's the power input which we've been given, you can now work out the power generated by the solar panel as being the power output. It's going to be the efficiency times the power input. So we know the power input, we know the efficiency, so you just multiply the two together, and you'll get 404 roughly watts to 3 significant figures. So you can put it to 404. I've shown you what it is to 5 significant figures, or you could even round it up to 2 significant figures, because the efficiency is not known that accurately. The efficiency is only 20%, okay? And that takes us to the next part of this question, which is using electricity again. So the circuit diagram shows how a light-dependent resistor, an LDR, can be used to produce an output potential difference that is dependent on the intensity of light. So the output potential difference is here, and it goes to a motor circuit. So we're going to run a motor with it. And the output PD is connected to a motor circuit that operates the movement of the solar panel that we've just been considering in part A. So we've got 24 volts across 2 resistors. One's a light-dependent resistor, and the other's a fixed resistor. Yeah? So initially the motor is switched off, and the light intensity increases, and the resistance of the LDR decreases to 750. Yeah? So the resistor LDR goes down to 750, and that's over here. So we know that when the light intensity in this scenario, the LDR's resistance is less than the fixed resistor, which is 1 kilo ohm. So 1000 compared to 750. Okay? So you can work out how much of the 24 volts is going to go to the output circuit. and it's going to be 1000 out of 1750 as a fraction, because the 1000 ohms is what's determining the ratio that will be output. Okay, so be put out. So 1000 divided by 1750, which is the two resistors added together on the bottom, yeah, will determine that the output will be 13.7 volts. And the question is saying the motor switches on when the output voltage is above 13 volts. So you've got to work out whether this change in light intensity causes the motor to switch on. So the answer is yes. So the motor will switch on because the calculated output voltage is 13.7, which is greater than 13, and that will get you the 3 marks. And here you come to the final question, end of the exam, 20 marks for section B, 60 marks for section A, and this gets you your final 80 marks for the exam, and you can determine what grade you think you deserve if you look at the grade boundaries, because this is from 2019 and they're available online. C says, when light is instant on the LDR, electrons move to a higher energy level and they become conduction electrons. This causes the resistance of the LDR to decrease. A student suggests that this is an example of the photoelectric effect. The student is incorrect, is not correct. They're telling you that. Compare and contrast the photoelectric effect with the effect of radiation instant on an LDR. Well, they've actually told you the answer, that it just, the electrons move to a higher energy level. Here, they move to a higher energy level. I don't like the way that arrow went. It's not obeying my instructions. So it goes to a higher energy level in the semiconductor device. And that's another difference. They want you to talk about compare and contrast, means talk about similarities and differences. So between them. So they only go, the electrons only go to a higher energy level, whereas in the photoelectric effect, they actually escape from the surface. So the main difference is, the electrons are not released from the surface in the LDR. Yeah, an LDR is a semiconductor, and the photoelectric effect occurs with metals. Okay, so that's another difference. And then you can look at the mark scheme to see what else you should say to get the 6 marks. So I'm telling you the main differences. The similarities are both of them absorb energy from photons. Yeah, the photoelectric absorbs the photon energy and releases the electrons with kinetic energy if the threshold frequency has been reached. So in other words, if the energy is equal to HF naught, which will be the minimum frequency needed to release electrons. So both absorb photon energy. So we talk about the differences. You also have to talk about the similarities to be able to compare and contrast, as it says in the question. So we're going to go straight to the mark scheme and have a look at what they accept here for the answers in this question. So you don't have to take my word for it. And here you got the similarities, 6 marks. An electron absorbs a photon. Yeah. So in both cases. Or electrons gain energy from a photon, same wording. Photons need a minimum amount of energy. Yeah. So in other words, even with both of them, you would need a minimum amount of energy from the photon that certain photons would not be able to, even in the LDR, to push the electrons into the conduction band. So light must be above a certain frequency for both of them. And increasing the light intensity increases the number of electrons released per second. either in the photoelectric effect, as in released from the surface, or released as in from being bound electrons to being conduction electrons in the LDR effect. Evidence for the particle model of light is a similarity as well, which I didn't consider putting in my discussion. And then the difference is in the photoelectric effect, electrons are released from the surface, but the electrons remain still within the LDR. They just go to the conduction band. And the photoelectric effect occurs in metals, whereas an LDR is a semiconductor device. So you see 1, 2, 3, 5, 8 ways of getting your final 6 marks in this paper. Okay, so I hope you found that useful. I'm now going to go backwards through the first part of 16A and B. So you can pause the video and mark your own. I think there was a mistake here in the typo. I think I've corrected it. Hopefully you can read that. And then question 15 was the 8-mark question, which was about potential energy, kinetic energy, momentum. So it's about forces and materials, forces and materials combined. It's a good combination. In fact, in the IAL, you have modules on mechanics and materials together. So they'll be very useful for you to go and practice. So I hope you found this useful. We did 2 longish videos to cover this 2019 paper with the full explanation. So it's not like some of the other run-throughs where they don't go through things in detail. They just try to get the answers done quickly. If you found it useful, give it a like, share it with your friends, and subscribe. More videos coming for linear and for modular soon, and for GCSE if you've got brothers, sisters, cousins who are doing it. So thanks again for watching, and hopefully see you in the next video. I was going to say something else, but it slipped my mind. Okay, thanks for watching. Bye for now.